But I'm very excited to talk with you all about some social networks. This is something that I've been really interested in for more than 10 years, but have delved more deeply in the last about 8 or so. And just networks is a representation of relational data. If you want to think of this, sorry, the chat is throwing me off. Anyway, so the networks are a representation of structural data. It's a way of going from thinking about a vector of relationships in your typical regression analysis or general statistics, thinking of the interdependencies between relationships. So it starts getting at questions of why are friends of friends more likely to be connected? Why is the enemy of my friend likely to be my friend? And so it gets at the relational dependencies within these data. It can provide tremendous insights into understanding social processes. It doesn't really matter what the nodes and the edges are, I want to add. So you could be looking at connections between synapses in the brain all the way up to country relations. And so we're going to go up to that higher level because I'm a sociologist by training. And I want to start off with just some of the basics of how we can import data, how we can begin to visualize it, and then get some basic descriptive statistics out of the networks. So sometimes, if you are lucky, you'll get a nice clean file that already has the relationships already presented for you. So this is an adjacency matrix. It's a square adjacency matrix where all of the rows and columns are identical, and it's valued because it's showing the number of times that these two people have connected together. It is symmetric, so the top triangle is equal to the bottom triangle. So that means we also don't have, well, not necessarily, but here we don't have a directed relationship. So we're not looking at how many times did Josh try to talk to David. We have the number of times that Josh and David spoke to each other. So we already know it's a matrix. We want to bring in some of the node info. Yep.
Do you mind zooming in just a little bit?
Not at all.
Or increasing the font.
All right, I'm old. Ben, how do I do that? Sorry, y'all.
I think it's good now.
Does that help everyone? Okay.
Oh, Control plus. Sorry.
How's that?
Perfect. Thank you.
Okay. Thanks you all for bearing with me. I apologize if this does come off a little rough. It's been a lot of COVID modeling the last 2 weeks. All right. So the package network has many different pre-built networks into it, which is really nice. The Emergency Management Organization is a set of organization collaborations over time during Hurricane Katrina. So it's really interesting to look at the longitudinal collaborations and just where they're from, the different attributes there. And the Florentine wedding data is a famous data set from Paget at University of Chicago, where he went through historical records of basically the Medicis, if you're familiar with that. So it's pretty interesting if you just plot the flow data after you load it. But you'll see some of these familiar names, the Pazzis, and then obviously the Medicis. So this has gotten much more interesting to talk about after that show come out. Hopefully some of you actually watch this, but so we can just do plot flow. Sorry, we'll get to that. All in good time. As we want to start looking at some of the relationships between our objects, we can get a quick description of the data. And so this is going to show us the network object, because these are a special class within R. So telling us the number of vertices, whether or not it's a directed or undirected graph. So you could have symmetric ties, just number of times we spoke versus number of times that I tried to speak. You have loops, so these are ties within oneself. Bipartite networks are showing you if you have two different sets of nodes where the relationships are only between sets. So if you had individuals and locations and you're looking at how many times a individual was at a specific location, that is one type of bipartite network. Then total edges is showing you how many connections, the sum of that adjacency matrix. And this is a way to get some quick summary of those relationships. So the dyad count is just telling you how many connections there are, how many total dyad pairs there are out of the number of vertices. And then you can get just how large is the network. So the basic things here. So you can plot the beginning of the relationships, and we can move around the names, we can move around the vertices. I'll get to that here in a little bit. The default plotting is a Fruchterman and Reingold spring embedded. So it's pulling groups together, it's pulling nodes together based on how proximate they are, how tied they are. So if we added a tie between Emma and Gil, this entire triangle would sort of fold in over this way. If we added a tie from Caroline to anyone, she would get pulled in. So it is very much a spring in the literal sense of stronger forces pulling the nodes together, weaker forces pushing them apart. I'm going to show you the circle layout. I would highly recommend that you never use it. It just doesn't really show a lot of information. Occasionally you can get a cool figure if you add some curve to the lines. I have never found it to be useful. Let's just keep going. So there are ways that you can create just an empty network and then add edges to it if you don't want to go through the process of loading a adjacency matrix or creating an edge list. Edge lists are preferable if you have a large sparse network because it just takes less memory in R. So if we wanted to start with a social distancing network, we have 5 nodes that aren't interacting at all. We can then begin to add an edge between the different vertices. This is going to just show you again how many edges we've added and the number of vertices, all that basic information. You can think of it like the summary command. And then we plot with our new relations that we went from a social distance to a kite or stingray. Similarly, we can remove edges. This is really useful if you're trying to clean data. I'm going to skip that for now. And then this is how you can start looking at, is there a tie between particular ones? Do you want to delete particular relationships? So Gil or isolate is now leaving us entirely. Do I check Q&A? No, not for me. Any link to this code? Yes, you can get linked to this code. That's just another way of getting the another way of showing the data as a plot. And you can get particular relationships if you want to think of the strengths. So remember when I showed you the relationships here, if you had values as opposed to a binary, that would be giving you the strength. So here we have the actual strength, and you can plot that using line thickness if you wanted to show the strength of the ties between particular vertices. You can also start bringing in attributes. Attributes are really useful as you start coloring vertices to look at additional information. We have a set of all of our different attributes here, and you can load in the relationship. I'm sorry, you can load in the vertex attributes using the %v% command, and that'll then call them. So we're getting to the SNA package. My preference is for SNA, as Ben said at the beginning, because my advisor wrote it. And so when your advisor writes a package in graduate school, that's pretty much what you use until you develop something better. I decided to just use what he built and develop my code on there. So most of my background is with exponential family random graph models, which builds on SNA and ERGM. And I'm happy to send out links that have the additional tutorials and introductory material for advanced network analysis, if that is of interest to people. So starting with density, density is just literally the number of ties over the total number of possible ties. In an undirected network, that's n squared minus n over 2. So you take the sum of the total number of edges and divide that by that formula. In a directed network, it's n squared minus n, just because you have twice as many relationships since it's not duplicative values in a symmetrized matrix. So the density is showing you that value. And I want to be very clear in this. This was shown in the late 80s, I believe, by Mayhew, that you do not want to compare density of networks of different sizes. It's really not a adequate way to compare, because the size of the network, you have a quadratic in the denominator. And so really a better way to think about comparing connections between disparate networks of different size is a centralization index if you scale it properly, or simply mean degree. And if that doesn't make sense, there are some other notes in here that will help you with that. And please ask during the Q&A. So I mentioned earlier about how you can have an edge list. And the edge list is just the actual ties that are there. So rather than having all of the sender receivers listed in a square matrix, which is not a big deal when you only have about 20 to even 50 nodes in a network. But as you have much larger networks in the order of thousands, you're wasting so much memory by having a bunch of zeros. So the edge list is a really nice way of making a more compact matrix that you can then work with. It's also typically a lot easier if you're writing code to create a matrix of just bringing in the values like this, as opposed to needing to do like an IJ going through and creating that entire matrix. So we can get the vertex names here, and then we can plot. We can get the socio matrix, which is again just basically it is the same thing as an adjacency matrix. So just showing us the relationships here. And I already said that. So now I want to do some visualizations. Let's go back to that network that we had of the friends that were talking with one another. We're going to use sex stereotype colors for this. Just add blue and pink for the women and men, and then we can plot these relationships. And you see, by using the vertex color, node colors, you're then able to see those relationships. And if we want to change the size of the nodes, vertex sex helps you with that. It's character expansion. And then if you can do label positions to have the name spin around. Notice that the network is moving every time that I plot it. You can set seed if you want to hold that, or you can actually save your coordinates, which we're going to get to here. So I already loaded this. This is getting at the Correlates of War project. And we have a lot of different countries, a lot of wars in 1993, unfortunately. But you notice that there's quite a few isolates that aren't involved in any of this. And let's bring in some of the names here. And so you can use the labels, or you can also pass it a vector of your own choosing for the labels here. Here is, I apologize. This is the one that is actually getting you the militarized dispute. So if you can see here, we have a lot going on in Eastern Europe. Russia's pretty prevalent here. This is right around the time of the fall of the Soviet Union. But all these isolates are really just taking up a lot of space. So I really like using display isolates false, because it just doesn't, depending on the graph that you're using, it's not giving you additional information that it's going to really help you understand the overall structure. So we see that we have one really large component and then a couple dyads, and then smaller sort of pairs that are going off. Again, we have our the different ways that we can show it. This is a circle. I think this helps you understand why I'm so down on that general sort of figure. And here is what I was talking about earlier about how you can capture the coordinates. So again, every time I plot, it's going to give me a different set because I have a new random seed. But if I capture the coordinates, just to prove my point. I need to make a new network. But if I set the coordinates to be my capture coordinates, it'll then keep that same one every single time, which is really useful if you're trying to show sort of transitions over time, because then you can keep the nodes in the same place without having them dance around in your screen. You can also customize using an interactive equals true. And now you can just click on a node and move it to wherever you want. And now I have customized coordinates. So if I go back and I plot this, now I plot the wrong network, but you see it keeps that structure. From here, it starts getting into degree centrality. And so these are ways that you count how central specific nodes are within the network. So you can get degree, which is just literally the number of connections that they have in a directed network. In degrees for the number of connections coming in a directed network. Out degree is the number of connections that they are sending. So you can think of in degrees the number of times a country was invaded. Out degree is the number of times that a country did the invading. And it's useful to plot these against one another. You get a sense of where the nodes fall within. Are they more aggressive or? And so now we're plotting these as the names of who's getting invaded more, who's going out more. So I realize that I'm at the time, and I apologize I didn't get to go through more of this. I will share this code with Ben and get this up for everyone. So at that point, do we go to Q&A? I feel like the old grandpa. This is weird. I'm just like yelling at the computer.
So Nolan, somebody asks about LinkedIn data. Would there be a way that we could download the connections people have on LinkedIn to plot the networks, such as your first example?
Oh, absolutely. I mean, if you have the API and you can download that data with a large network, I would absolutely recommend using the edge list as opposed to creating the full adjacency matrix. So then each row, or I'm sorry, column one would be the sender, column two would be the receiver. If you want to think of it as a directed relationship of who's talking to whom, since friendships are mutual on LinkedIn, you wouldn't even need to bother with a directed network. But then you could start looking at the relationships of like who's most central. And in networks, centrality obviously depends on the connotation of what you're looking at. Are you central because everyone is high-fiving you, or are you central because everyone is throwing tennis balls at you? Like the meaning of centrality differs based on the context of the network. But in a LinkedIn network, someone that's really central has a lot of friends. You could also think about if they have a high betweenness, that is that they lie on a large number of short paths. So that is the distance between multiple networks or multiple individuals within the network. So this person, Russia, would be very high betweenness because it lies on the paths between a lot of the other networks. So they are then considered power brokers within a network like that because they're able to connect individuals with disparate information. So I hope that helps. And please feel free to email me. Happy to talk about that more. That'd be a really cool analysis.
On that note, Nolan, how can they contact you?
NolanEPhillips@gmail.com. I guess I should probably.
Do you mind typing that in? Yes, perfectly. And going back to the original question,